Okay, I want to go through an example of how to find the rotational inertia whenever we have multiple rigid bodies, which is kind of, here's the situation I want to use. So if our axis of rotation is there, and I have basically a thin rod with a hoop at the end of it, and it's going to rotate around that axis. All right, so if this was the axis and this was the thin rod, it would rotate this way around that axis, and there'd just be some type of hoop at the end of that. And how do we go about doing this, right? It's a combination of the parallel axis theorem and how you just add the rotational inertia for any particles together. So we basically have to find the new rotational inertia of the thin rod and the hoop separate, and then you just add them together. So of a thin rod about its center, we can look that up, and we find that it's 1/12 ml squared, where L would be the length of the rod. For the hoop, it's 1/2 mr squared if it is rotating around its center axis. All right, so like spinning a roll of tape on a table or something like that. So it would just rotate that way. All right. So for the rod, this 1/12 is rotating just around there, and the hoop is rotating around the same kind of central axis there. All right, just to get a visual again, that roll of tape is just going to be rotating that way along an axis, kind of like spinning it. It's not the rotation like it's rolling. All right, so now what would happen if we slide the rod so that it rotates that way? So instead of it spinning around its center, it's going to spin around its very edge. Same thing with the hoop. We're going to move the hoop, so it's now going to spin there. So we have to figure out, we would be able to figure out the new rotational inertia of these. And let's do that just so we get used to the parallel axis theorem. Parallel axis theorem is that the I of the center of mass, whatever the normal amount is, so this would be the center of around the center of mass of the rod, all right, plus mh squared, where h is going to be the distance that we move the axis, right? So here we're moving the axis half of the length. Sorry, looking at my video, it looked like it stalled there. So just to reiterate, this is the parallel axis theorem. The h here stands for how far we move our rotational point, our axis. All right, so we're moving it from the center of mass over to here, which would be half of the length. Okay, same thing here. We're only moving it a radius away. So we're going to solve for the new center of mass of each of these. For the rod, we would take what it is around its center of mass and add whatever mh squared is, where h is 1/2 of the length. And if we work through that, we did that before anyway, so this is 1/4 ml squared. It's So you make that 3 over 12. You get 4 over 12, which is 1/3 ml squared. And that would be what it is for the rod, about this point. For the hoop, take the 1/2 mr squared, plus we moved it just an r away, plus mr squared, and adding those up, I think it's 3 over 2 mr squared. So the total of, if we were able to take these two and kind of put them on top of each other, should have did that with this one too. Alright, so I'm going to actually draw it right here. So what I'm talking about is if we took the rod and then attached the hoop to it like this and still rotated both of those over that axis, you would then just take both objects, rotational inertias that are separate, and add them together. So it'll be 1/3 ml squared plus 3/2 mr squared, and that would be the rotational inertia of that object. Get them off the page. Alright, so just take this one plus this one, so you're just basically adding them up like particles. Alright, if we did the same thing for this, where we put the hoop and attached it right at the center and rotated it that way, you would do the same thing. I'm going to come over to here now. So this is not using the parallel axis theorem. You're just adding up the eye of the rod plus the eye of the hoop. You know, and this was the original, so these are the original values here. 1/12 ml squared plus 1/2 mr squared, and that would be I total there. Alright, so not too bad, right? Well, what we have going on in this situation right here is we have our long rod moved and rotating about its edge, just like we had here, but then we take the hoop and we attach it to this end of the rod. We don't have to do anything for the rod now, we just have to figure out for the hoop. Alright, that's what we need. So that hoop would just be around some axis, rolling around it in space. And that's a distance L away. So to find the new value for the hoop, we'd have to take the original of the center of mass plus mh squared, where the center of mass was 1/2 mr squared. And now we've moved this, and this is around its center. We moved it an r away plus an L. Right, so this edge is L away, but it was originally right there, so it's an R plus L away. And that would be the new rotational inertia of the hoop spinning around that axis in space. So to get the total, just take what the rod is at that axis, which we just solved for is 1/3, plus whatever it is here. And that's it. So it's the parallel axis theorem for each individual rigid body, and then you just add them right up. That's it for this video.